Hi, I'm Sam Roberts from Roberts Geospatial. Welcome to the first of 4 videos in a series where I'm going to discuss modern raster technology. So the first part we'll be looking at the structure of a modern raster, then we'll be looking at interpolation of raster data, then raster statistics, and finally we'll be looking at the design of the raster engine in MapInfo Pro. So let's look at the structure of a modern raster. So a modern raster is a significant evolution from the old grids and images of the past. So it differs in its geometric complexity and in flexibility of its geometry, in its data storage flexibility, and in the data compression options. Significantly, a modern raster ought to be able to support rasters of virtually unlimited size and provide linear time access to that data at any scale, which it will do through the exploitation of the overview resolution levels or the overview pyramid and the corresponding underview resolution levels. So a modern raster will provide efficient storage by supporting sparse rasters, and it will offer lossless and lossy compression options and a rich selection of storage data types. And it might also support the temporal dimension and cell editing. This diagram on screen represents the geometric structure of a legacy raster, a simple grid or a located image. And you can see that it's very simple. It's simply a rectangular array of a fixed number of rows and fixed number of columns of cells. So you would completely define this raster by specifying the bottom left origin coordinate perhaps, the number of rows and number of columns, and the cell size. And in some cases you would also specify a rotation so that you could rotate the raster around the origin. A modern raster extends that concept. So instead of having one rectangular array, we have a extensible and editable sparse matrix of tiles, where the tile is equivalent to the original legacy raster grid. So you can see that in this diagram. We have a tile origin, here represented by this cross, and then tile boundaries represented by these red lines. And in each tile there's a fixed number of rows and columns of cells. Those cells may or may not be valid. So here are some valid cells and here are some invalid cells, but within a tile each cell will be stored. However, if you have tiles that have no cells in them whatsoever, like this tile here, then there may be no requirement to store the tile at all, and so that tile may take no storage overhead at all. Taking that concept a little bit further, it's also possible to have a variable cell size. So working from the assumption that the cell size should always be chosen to suit the density of the data observations from which you've created the raster, then this would allow the cell size to vary across the raster to suit the local variations in the observation density. So in the MapInfo system, that is supported at the tile scope. So a tile may use the base level cell size, that's the defined standard cell size, or it can use some higher multiple of the cell size, as long as that cell size meets the requirement that it perfectly divides into the tile with an integer number of rows and columns. And you can see that represented here, not particularly well, but here we have a high density of cells, lower density of cells, and even lower density of cells, and no cells out here, no tiles out here. So let's look at the data structure of a modern raster. We're looking up here. Folder, file, field, event, band, and component. So legacy rasters contained a single data band, and that was soon extended to support multiple data bands, which would all be of the same data type and the same geometry. A modern raster has a deeper hierarchy. So most legacy rasters were stored in multiple files. Some actually required the use of an entire folder on the storage device. So a legacy raster would often have had an ASCII header file of some description and then one or more binary data files. In addition, there would often be externally generated cache files for things like overviews. There would be other metadata files, for example, to support the target GIS system. And in MapInfo, that would be like the tab file, for example. A modern raster is more likely to be contained in a single file. That makes it more easy to transport, more easy to copy, more easy to share. So legacy raster formats were often designed for a particular type of data, for example, imagery or continuous data, and then over time they were repurposed to store other classes of raster data. Consequently, for some formats, it's not always easy to identify what kind of data is in the raster, and therefore it's not easy to know how to present that data to a GIS user. And the best example of this is the TIFF format, which can store a wide variety of data types, data classes, but isn't very good at identifying how that data ought to be presented and what that data is. So the field concept has been introduced in the modern raster to provide a high-level definition of what class of data is stored in the raster, and also to allow multiple different classes of data to be stored within a single raster. And in the MapInfo raster system, we recognize 4 different field types: continuous, and imagery, classified, and image palette. So they're kind of split into 2 groups, where cell data values acquired either by value or by reference. So if it's by value, that means that the cell contains the data value. It's unmodified. You just have to read that cell data out and you've got what you need. When it's by reference, each cell only contains one piece of data, and that is an index into an external table. So this table is a bit like a database. It's got rows and columns. So the cell it contains a zero-based index which takes you into a row into that table. So when you read a cell value, it reads the index and then goes off into the table to acquire the band from that table. So fields help us distinguish between by value and by reference access. They help users identify what kind of data is stored in the raster, and also they help programmers. And they allow multiple kinds of data to be stored in a raster. So here are some example images from the 4 different fields. So at the top here we have a continuous field. So continuous fields are the most general containers. They support multiple bands. Each band can be a specific data type. And the data varies continuously from cell to cell. So this is terrain data, LiDAR-derived terrain data with bathymetry. The next one is an image field. So an image field contains a color band. It's usually going to be red, green, blue, or RGB, or RGBA, where A is alpha. And again, the color varies continuously from cell to cell. Down here we have an image palette. So again, it's an image, but the data is stored by reference. So there's a color palette, which is our table, and each pixel only stores the index into that table. So that can be a more efficient way to store images that have only a small number of colors in them. However, there are disadvantages to using that system as well. And over here we have a classified raster. So this is a land use raster. So again, it's by reference. Each cell stores an index into a classification table. Classified rasters haven't been used a lot in the past, but I think that in the future they should be used a lot more. So for example, you can take a polygonal GIS table and convert it almost losslessly, into a classified raster. So all of the columns in the table, including strings and times and other data, they can all be copied into the classification table. And then the polygons are rasterized into pixels, and that's all stored into the raster. So they have an alternative to a polygonal table with all of the information in the table preserved. And some people say, well, won't that be huge compared to the original polygonal table? And the answer is usually not. So classified rasters tend to compress very efficiently, often a 100-to-1 ratio or better. And so what I've observed through my work is often the classified raster is a similar size to the original GIS table. So continuing on data structure, let's look at events, bands, and components. So bands are used to store data of a particular type. So it might be integer or decimal or color, or some more obscure type like complex numbers or time and date or a string. So a field might be single banded. For example, an image field has a single color data type. It might be multi-banded, or it might be many-banded, and by many-banded I mean have hundreds of bands. So for example, hyperspectral imagery. And the difference between multi-banded, where you have a few bands, and many bands, where you have a few hundred bands, is really about efficiency in your raster engine. It has to be able to cope with that situation efficiently. The data type of the bands can be different for each band. The cell validity can be stored once for all the bands of the cell, or it can be stored for each band of the cell individually. And then components are derived from the band data type. So if you have a multi-component data type, a band data type, then the raster engine can expose additional virtual bands to you, which are the components of that band. So for example, if you have RGBA as the data type, which is color, red, green, blue, and alpha, then those 4 color components can be exposed as virtual bands. Other examples are complex numbers, where you have the real and imaginary band, or a time data type might be able to be split into year and month and day and hour, etc. Events provide rasters with a time dimension. So you can store data in one or more events in a raster, and you can assign a time to that event. So you might have 16 events, and you assign a time to each one of those events, and then you could animate that raster by cycling through those 16 events. So it provides a time dimension. It can also be used to edit a raster non-destructively. So when you add an event, you're adding data all the time. You're never destroying data. So for example, so you can use it to edit data without destroying what you had before. And then the raster engine can be used to acquire that data at some point in the editing process, or at the end of the editing process, the finalized raster, whatever you want. So the resolution structure is an important feature of a modern raster. So you've got the base level. The base level has a certain cell size. That's the level at which you populate your cells in a raster. So any edits that you make, any events that you define, the cells will all be populated at the base level. And in a legacy raster, that was the only resolution level that existed. But in a modern raster, it will also have overview resolution levels and underview resolution levels. So overviews, or the overview pyramids, sit on top of the base resolution level, and each overview is progressively lower resolution than the one before it. So an overview is created from the underlying resolution level by downsampling. In an overview level, the cell size is going to be larger than the base level, and it increases as you progress up the overview pyramid. Eventually you'll get to a point where you only have a single cell in the overview pyramid, and so the pyramid comes to a natural end. So the size of each overview level is going to be smaller than the preceding level, and in a power of 2 system, each overview cell might be created by averaging the value of the 4 cells that perfectly overlap it in the resolution level that's below it. So overviews are expensive to prepare. You have to go through the entire raster and then go through each level. They should be prepared in advance, and they can be either stored in the raster or cached in a separate file. So if you're using ArcGIS or QGIS, using the GDAL system, you'll have OVR files which are caching the overviews. In the MapInfo system, you'll have a PPRC file which is caching the overview. And in some raster formats like MRR or Cloud Optimized GeoTIFF, the overviews will be written into the raster file and will be there for you at all times. So there are some wrinkles in generating overviews. One of these is preserving data presence upwards. So if you have a raster that at the base level is very sparse, when you go to the next level up and the next level up and the next level up, the invalid cells may begin to dominate the raster, and at some point you'll have no data left in your overview. It will completely disappear. So there are some rules that you can apply to make sure that you preserve data as it goes upwards so that you've always got something in your pyramid. If you're merging by data that's stored by value, then you might average the cells underlying the overview level in order to acquire a new value. You might filter. There are other methods that you can use. If you're merging by reference data, then you can't average. You have to choose a value. So you'll choose usually the most common value that's underlying the target cell. And then there are some other data types which you can't merge. So these things are non-combinable. For example, if you have a Landsat scene, it will come with a band, an information band, which is a bitwise integer band, and each bit records whether or not some certain thing is present in the data. So there's a bit for water and a bit for cloud and a bit for valid or invalid, a bit for noise. That kind of data can't be merged, and so it has to be treated as though it's like by reference data. So underviews are higher resolution levels, so they're kind of underneath the base level, and they're generated by upsampling. So you need to choose some kind of interpolation method in order to generate your underviews. So it could be nearest neighbor, it could be bilinear, it could be bicubic. They're the common methods. So in the MapInfo raster engine, underviews are created on the fly, and they're not permanently stored. They'll go into the cache and they might get reused, but they're not permanently stored in the raster file. And that's because there's no limit to how many underview levels you could create. There's an infinite number of underview levels. So in a rendering system, overview levels are what you see when you zoom out, and underview levels are what you see when you zoom in. So finally, a word about storing a modern raster. A modern raster has so many things inside it. It's going to have tiles which will contain data in multiple bands. There will be events. There will be tables like colored palette tables. There'll be classification tables. There'll be overviews. There'll be statistics and other metadata. There'll be spatial maps which make it possible to efficiently access the data. A lot of individual components, and all that has to be put together into one or more files. So the approach that I took in the MRR format was to use a single file, but that file is a special file. It actually has a file system inside it. So an MRR actually consists of many files, possibly millions of files, but they're all stored into a single file on disk, so you don't see any of that complexity. But whilst you don't see the complexity, because it's there, it means it's modifiable. So you can go and change any of that data, you can add to it, add events, edit cells, do whatever you want, change metadata, change properties, and update that file, and that can be done efficiently. The other important thing today is compression. So rasters are getting very large, and it's important to use compression to reduce the size that you require to store those rasters. And compression can either be lossless, in which case there is no loss of information, or it can be lossy. So generally you'll use a lossless data compression algorithm for everything in your raster. So for example, that might be LZ4, which is very fast, or it might be LZMA, which is sort of best-in-class compressor for making the smallest possible files. If you have image data, then you have the option of using lossy compressors, which throw information away in order to make the file much smaller still. So lossy compressors include things like JPEG, JPEG 2000, which uses wavelet compression, which is the method used in ECW, Mr. SID, and so forth. So it's entirely up to you. My view, for what it's worth, is that I think the lossy compression of imagery is not as useful as it used to be. So we have plenty of storage available. It's much cheaper than it used to be. We can afford to keep imagery in its highest possible quality. And I think if you're going to be using your imagery for applications like machine learning and AI, well then it's garbage in, garbage out. So if you have highly compressed imagery, you're not going to get the same result from your machine learning algorithms as you would with high quality imagery. So that's my view. Take it or leave it. So thanks for watching. That was the structure of a modern raster. In the next video, we'll look at interpolation methods. See you then.